Okay, so now we'll be doing the question more asymptotics potpourri. So the first algorithm we're going to be looking at is counting sort. So as a brief review, in counting sort, we take an array of elements, such as this one, and count the number of each element. And in this array, the radix, or base, are the digits 0 through 9. So the first thing we'll do is we'll take this array of elements and we will count how many of each element there are. So for 0 through 9, we're going to count how many of each of those digits there are. So we will have an array that looks like this. So here are the counts, and this required me to go through the array once. So now what we do in counting sort is we change this counts array into an indices array. And the way we do that is by adding the previous value. So 0 plus 0, well, this is still 0. 1 plus 0 is still 1. But 0 plus 1, this we now change to 1. 1 plus 3, we now change this to 4. And so on. So this is the array you get. So now that we have these indices, we can create our resulting sorted array. And our resulting sorted array will have the number of elements is equal to in the input array. So in this case, that's 9. So I've drawn an array here with 9 elements. So you may notice that in this resulting array, I have the values going from 1 through 9. And the reason for this is because in our indices array that we created, we're also going from 1 through 9. So now to fill in this resulting array, we're going to start from 6 and we're going to say, okay, 6 is here, so we're going to go to the 6th value in our indices array. We're going to see it says 7. So we're going to put 6 in the 7th place, and then we're going to change 7 to 6. Then we're going to go to 4, and we're going to look up 4, and 4 has 4. So we'll put 4, and then we'll change this to 3. Then we'll go to 6, and it has 6, so we'll put it in 6. And then we'll change this to 5. We will go to 5, and it has 5, so we'll put it in 5, and we'll change it to 4. We'll go to 4, and it says 3, so we'll put it in 3 and change it to 2. We'll do another 4, so we'll change this to 1, and we'll put 4 in 2. And then we'll go to 7, and 7 has an 8, so we'll put it in the 8th place, and then change that to 7. We'll go to 2. 2 has a 1, so we'll put it in the first position and change its index to 0. And then finally we'll go to 8, which has position 9, and then we can change it to 8. And we're done since we filled our array. So notice here that we had to go through this array once in order to get all the counts, and then we had to go through our counts array once to create our indices array, and then for our result we had to go through our initial input array again. So our input array, which we went through twice, is of size n. Let's say the number of elements is n. And our indices array is the size of our radix, which in this case, let's call it r. So therefore, our runtime for this problem is theta of n plus r. Now realize that this is the runtime for both the best case and the worst case, and this is because regardless of how your input array is sorted, you're going to have to go through it once to get all the counts, and you're going to have to go through the entire counts array in order to get the previous counts. And then of course you also go through the input array again to put your result in order. Also notice that we put this 6 over here and we put this 6 over here, so we can see that this sort is stable because keys of the same value maintain their order. Okay, so that's it for counting sort. Let's move on to our second algorithm. So in LSE radix sort, we're given an array of some keys which are based on a radix. They all have a base. So in this case, for these elements, the base or radix is the set of letters A, B, C, and D. So recall an LSE radix sort, we'll start from the least significant digit and sort the keys according to that digit. Then we'll move on to the next digit, the next one, all the way until we get to the most significant digit, after which we'll be done. So to sort each one of these digits, we're going to use counting sort. So that means that if we have W digits, so W would be the length of the longest word, where each one of these is a word. we'd have to apply counting sort W times. And we know the runtime of counting sort, so the runtime here would just be W times N plus R. Again, where N is the length of the input array, so the number of words or the number of elements, and R is the size of the radix, which in this case is 4. So the values that each of these digits can take on in the words. And in this case, the best case and the worst case runtimes are the same because we start with the least significant digit. So we won't know really the ordering of the elements until we're at the most significant digit. And yes, this is a stable sort, and that's because during each time that we're looking at a digit, we are making sure to keep the input order that was given to us. Okay, so I've just finished filling in the best case, worst case, and stability. So let's move on to our third algorithm. So the third algorithm we're going to be discussing is MSD radix sort, and this is kind of similar to LSD radix sort. So we're going to be sorting each digit, and each time we're going to be applying counting sort, but this time we're going to start from the most significant digit and move our way down to the least significant digit. So again, we're applying counting sort W times if we want to go through every single digit. So that would be theta of W N plus R. But this is only the runtime for the worst case. This is because in the best case, we don't have to go through all the digits. But in the worst case, we would have to go through all the digits. So for a best case example, consider a list of elements where all of the most significant digits are different. So if you had A, D, C, and B in this example, for instance, we would already know the ordering of the elements without looking at the rest of their digits. So in this case, we're only doing counting sort once, which is theta of N plus R runtime as we discussed before. So this is the best case. And again, the worst case would be when you have to apply counting sort to every single digit. So the stability of MSD radix sort really depends. If we had an extra memory buffer that's the size of our input array, it would be stable, but if we didn't, it wouldn't be. And the reason for this is that when we are sorting an MSD radix sort, it's slightly different than an LSD because we are forming sort of bins. In LSD radix sort, for every digit we sort the entire list of elements. But for MSD radix sort, we sort the list of elements in bins, and the bins are created from the previous digit sorting. And in order to create these bins, we'd have to do some swapping. And that swapping doesn't guarantee that we would keep the same initial ordering. But if you had an additional array of size input, then we would be able to ensure that we are moving things in the order of the input because we no longer have to swap elements in order to group the bins together. So the stability of this algorithm depends. Okay, so now we have the table filled out, and that's it for this question.